Yeah, hi. I'm talking about DFEM, which you might have heard once or twice today already. And the title of the talk is Differentiating Large-Scale Finite Element Applications with MFEM. But the TLDR will be that you actually don't. Like you but you will experience what that means during the talk. So the usual approach to automatic differentiation, like what is out there or was out there until not so long time ago, is that automatic differentiation is often perceived as like a black box tool. So you have your tool set that you apply to your either the source code transformation, or you apply it as like a dual number type to like the whole code and the whole application at the highest possible level. So this would be your tools like JAX or PyTorch, or all the different C and C++ tools that are available. That leads to a low implementation barrier, which is good initially, but as soon as you reach problems that are actually interesting, you will lose the impression that the low implementation barrier is a good thing. So the AD tools then have to work through like complicated program structures, as you can imagine, non-trivial object types, and the worst thing is actually to like differentiate the communication layer, like MPI. And this introduces infeasible overhead in applications we deal with, even for the smallest interesting problems. So we must balance the implementation effort with automatic differentiation convenience to ensure the least overhead possible, and carefully decide on the entry points where automatic differentiation has to happen or actually can happen. And we still have to provide a clear and concise interface for users, because no library is worth existing without users, right? So the last fact is that GPUs usually make things worse. I wrote 100 times with underestimated guess. So our approach is to constrain automatic differentiation to the quadrature point level. So I showed you here the snippet of the last entry of our finite element operator decomposition. And if you haven't seen that diagram enough today, here's it again. So the global domain, the T vectors, and the P operator, prolongation operator, those would deal with MPI communication. So we have to avoid those at all cost. So AD cannot happen at that level, or the L, or even the E vector level. What we have to do is focus on this D operator, which is the operation, the physical operation on the quadrature point. At that point, it's actually not related to finite elements anymore what the automatic differentiation algorithms see. It's plain code, so it should be way more easy for those tools to optimize it and be efficient. So we chose Enzyme as our like performant optimization, automatic differentiation utility. You might wonder, why not our own implementation? Why not language specific? as you saw or heard in the previous talk, enzyme utilizes LLVM as its backend, and therefore, if you can write a front end for LLVM, any language that is translated into the LLVM IR can leverage enzyme as a plugin during and do automatic differentiation. So this opens up like a whole new concept of thinking about implementing automatic differentiation and also incorporating those kernels that are generated from it into MFEM or finite element codes in general. So another thing is that production codes are compositions of complicated physics. There is not just like diffusion, not just radiation, not hydro. There is a combination of a bunch of those, and a variety of domain experts work on specific parts of the code. So you have or might have multiple programming languages that have to work together. And it's already hard enough to couple different languages by themselves. And then also handling automatic differentiation is like a whole nother complication in that process. And the only tool that would make that possible would be boiling everything down into one layer that can communicate with each other. And that would be the intermediate representation. So material models lead to additional experts that only see and work on those specific parts of the code. So you can really isolate the parts that are relevant for the physics and decouple them due to the finite element operator decomposition into their specific domain. And the enzyme LLVM plugin allows us to use this complex combination of libraries that may be written in different programming languages, might not be able to be modified by certain people. So you can only deal deal with objects like binaries and don't have access to the source code. Or there might be legacy applications where you don't want to change code, and therefore most of the tools, the AD tools, don't even work. Like there wouldn't be an option. So what we did was we introduced the DFEM interface to MFEM, not as a replacement for existing things. It's more like an addition that allows you to couple existing MFEM tools and additionally use DFEM as another way of providing, let's say, a bilinear form, a nonlinear form to your physics code and extending the functionality, making derivatives easier. So as kind of one of the big things we set as a goal was, well, the minimum functionality that we have to show is, can this work on Hydro, right? So we have this mini app. It's not really, no, it's not a mini app, sorry. It's, what do you call it? Benchmark application, right? A proxy application, Lagos, which is the Lagrangian phase of an ALE shock hydro solver. And we replicated that in DFEM, first in explicit time integration. So these are results from the previous state. So that means that you not just have or you don't need to use DFEM and the interface to use it as an interface for automated differentiation. It might also make prototyping for other things easier, maybe not as performant, but simpler to understand and prototype. So first, we replicated Lagos and DFEM for explicit time integration. That was the state we already had. And then we extended the implementation to support implicit time integration for Hydro, including like the automatic derivatives from DFEM using enzyme that leverage all the functionality so that we can do something that we like usually never see. Like we have no evidence that there was ever like high order finite element implicit time integrate, like fully implicit time integrated Hydro simulation. And you can see in certain cases, I'm purposely not printing or writing the time to solution here because this is a work in progress. But you see, you get the benefits of implicit time integration, even for a Hydro code, without having the burden of hand deriving and manually implementing the derivative of the Q functions. Because this includes material models, right? They are not trivial. Well, this is ideal gas, maybe fine. But like real applications, they are not ideal gas. They might be 1,000 lines of Fortran, so good luck. And other things like artificial viscosity, those are differentiated through enzyme. There's an eigendecomposition in there. You either write custom derivatives for that, or yeah, this is it's such first it's a time saver for prototyping, but on the other hand, it can really enhance and extend functionality of application codes. Oh, I didn't talk about the implicit explicit difference. Well, so you see that in the explicit case, this is an RK format that CFL is limited to 0.5, which is very typical. You see the solver, it's adaptive. It chose to take 737 steps to reach the final time. And we chose the energy difference as some kind of metric to see if they do the same thing. And the implicit midpoint method, just second order, still one stage, takes like 100 time steps. But at every time step, you have to nonlinearly converge the full system because it's implicit time integration. So there's a trade-off, no free lunch. But it opens up the opportunity for research and for exploring new methods, right? Before the burden of implementing that was way too large to justify the time. So this is the AL overlay. The dashed lines are the original explicit code, and then the white solid lines are the implicit overlaid. The shock position is a little skewed, but like eyeball norm is fine. So as you may have noticed, a lot of those slides I already showed in other talks, and some of them were actually also from last year's workshop. But there has been a lot of development. First of all, DFAM is in the main branch, so it's available in your recent checkout. There are examples which demonstrate the functionality, the interface. There's a lot of documentation, and what is work in progress, or what are the next steps that we are taking to improve DFAM. First of all, we're going to introduce the automatic assembly of locus sparse matrices, element matrices, and then global hyperpar matrix to allow like the Jacobian assembly, so you can use preconditioners and are not just stuck with Jacobian vector product action. This, as you saw in the implicit time integration for Lagos, this is already in a branch. It just has to be polished a little bit, and then we can probably present it to the public. Then partial assembly. Partial assembly is this this word that is always associated with performance on the GPU. Everything you saw, or everything that I mentioned for DFAM, automatically dispatches to GPU, to any vendor that we support anyways. So partial assembly would, in the regular integrators, would require you to write the algorithm in that way, right? What this approach does is it kind of assumes an optimal way to cache the partial assembly data and then applies it on as an action. So you will get the benefit of partial assembly on any operator that you write in DFAM by just using DFAM. There's no, like, it's not in the current state, but imagine you start writing a new integrator in DFAM or operator, and you might not even use the derivatives for it. And then next week, I'm going to update, or next week, PR is merged. You will get the benefit immediately, right? And this represents another, like, the not just synergy, but advantage of those decomposition interfaces. So this also enables the functionality of transpose actions, the waving hand at the adjoint method for optimization. So you might recognize the theme here. All of the next steps work towards making optimization like the full process possible. And one thing I haven't shown to a lot of people, besides I get excited and DM some people on Slack, which is just-in-time compilation, which is highly experimental. But this is in collaboration with Georgis Georgakudis. They're laughing because I butchered the last name. So this is a performance. How do I put it? There still is probably a lot of doubt if JIT can actually sustain on HPC machines. The reason for that is usually there's a cache, a lot of data access to the drive or file system during a major run is not sustainable. So you usually try to avoid that in hot loops. Okay, I get that, but we got new techniques. We got LLVM as a JIT engine. We have virtual file systems in memory, etc. So the Proteus toolkit, which is also developed at Lawrence Livermore, introduced a source just-in-time compilation engine. So you load in a source file, you compile the Proteus toolkit does the compilation, and you end up with bitcode. So first of all, this can make functions that you execute faster by just making assumptions about linking or not linking with outside functions. You can inline a lot more than usual. And you can also run more optimization passes. So this shows a very simple function that you can manually take a derivative from, but it's still taxing in terms of execution. This is all execution on GPU. Those are MI300s on a similar system to El Capitan. And keep in mind, GPU kernel launches latency is around 5 microseconds. These timings do not include the launching of the kernels. So these are just the actual execution. And the doubt is, or the concern is, the bigger the number of nodes, the slower JIT would get because it's more taxing on the system. There might be communication going on, right? So as you can see, there is absolutely no difference in running the function in blue here or the JIT function on different number of nodes or ranks. So this is not like 10,000 node simulation, but this shows the general trajectory. The same is true for using JIT with enzyme. So in the JIT pass, you run an enzyme pass and you get a JIT derivative. This might also address a question from before, like we have a ton of kernels which are instantiated, and JIT might solve such an organizational problem. But yeah, it's probably a hot topic. Also, as you can see here in red is the JIT enzyme combination. And I'm pretty excited about seeing the plot look like this because there's really no difference in besides jitter in timing from 4 ranks on one node or 16 nodes or even higher. Like I hope I can put this argument or this doubt to rest with a little more computational time. Okay, so AD overview in MFEM. We utilize the decomposition to only do derivatives at quadrature points. We have a description for a parametric nonlinear operator, and we need to do the derivatives at quadrature points only. And this makes this whole DFEM interface possible. All right. Questions?
So you mentioned about your parametric nonlinear operator that you generate at the end, and I'm kind of interested in how. So if you, and I understand the point of this talk was around enzyme, but if you were to explicitly set up the action of your nonlinear operator and the Jacobian through key functions, do you see any kind of significant performance hit relative to like
a performance hit?
Yeah, or any difference in performance compared to kind of traditional
on just the regular action?
Yeah, comparing it to traditional MFEM integrators?
Well, let's say you compare a diffusion integrator or diffusion operator with the highly optimized partial assembly diffusion operator. Due to the fact that we have to be very general in DFEM with the current implementation, yes, there is a performance difference. It's not extreme, but it's noticeable. But let's say JIT is an appropriate way to solve that with certain heuristics, we would be able to either be on par or better. Yeah.
Okay, thank you very much.
Yeah.
Other questions? Thank you.
I'm trying to remember exactly what Lagos uses for the time step refinement. Did you change that at all? Or are you still using?
For the implicit part?
Right.
Yeah, so this was shown with no time adaptivity for implicit time integration.
Okay, so that
Yeah.
0 point, whatever the time step was, that was fixed up.
Right, yeah.
Okay,
That
I guess I
was
should have been able to divide, the
Yeah.
final time by the time
Yeah.
number of
No,
steps, but-
it's the exact, like it's one time step that is determined by the initial condition.
Okay. Yeah, I mean, I certainly could see if you had something adaptive that makes it easier for the nonlinear solver, then you can get that runtime you didn't show down, but
Theoretically.
yeah, sure. Thank you.
Oh.
So your implicit DFEM is just using DFEM to compute Jacobi?
Yeah.
Okay. Have you thought about how to do that if the problem is implicit defined? And do you have to still do some adjoint?
If the problem is implicit in time?
No, probably the solution is implicit defined based on some linear or nonlinear solve, and I'm interested in differentiate with respect to some physical parameters.
Yeah, you can do that. You mean so that's why we say parametric discretization. So parametric operator. Yeah.
But basically the differentiation has to go through the linear or nonlinear solve. Would that be possible? So let's say Laplacian U equals F depends on some parameters. I want to differentiate with respect to that.
Well, the D operator depends on rho, for example. If rho is your parameter, then the idea is, can you see that? Yeah. So you have rho here, but P, G, and B, and also the solvers on the outside are not dependent on rho, right? So the derivative of gradient of rho, just imagine this wouldn't be a U, it would be a rho. Then it just trickles through up to the D operator. So there is no need to differentiate through the solver. Or do I not understand the question?
Well, so you have to define agent. Okay. You still can use it, right? So the DFEM can still be used.
Yeah.
Okay. But I still have to solve adjoint, right?
Right.
Yeah. Okay.
Yeah.
Sounds good. Anyway, yeah. Thanks. That's my question.
Just to be super explicit about it, DFEM will be used to produce all the components that you need to put together in the joint solve. You still need to create and execute it, but it will be the Jacobians, the derivative with respect to parameters, that will be automatic.
Right. If you're a little adventurous, you can even get second derivatives out of DFEM right now. But